Okay, so I am most of the way through your exams. You'll probably get them back on Wednesday. I have to give a makeup today to a couple of people who had to miss for school stuff. So I'll get theirs graded, but I had 2 different versions. And it's really hard for me to tell how people do when I grade because I grade 1 problem at a time. So I just grade 1 problem for everybody, then I flip the page and grade 1 problem for everybody. So I don't have any sense of how any individual person is doing until I go back and total everything up. So, but so far things feel somewhat normal. There were 2 versions of the exam. I think you guys had the slightly harder version of the exam. It wasn't intentional, but I just noticed when I was grading that there were a couple problems that were, I was like, it was a little tricky. So we'll see how it all works out at the end, and then I'll talk to you guys more about it when I give it back on Wednesday. All right, so today we're going to start Unit 2, and we're going to start at Section 3.1. And this unit is going to be all about inverse functions, and more specifically, we're going to get into a specific type of inverse function, and we're going to talk about logs and exponentials. But before we can get into that, we need to kind of define what is a one-to-one function and what is an inverse function and how do they work. So we say, right, we said something is a function, right? We're just going to kind of abbreviate this that we've defined before, right? If every input value, right, maps to exactly 1 output, right? So for any value that you're allowed to plug in, it should only return 1 number back. And as long as that happens for every single value, right, we knew we had a function. And visually, right, we said we could test for a function on a table by looking at the input variables and nothing should ever be repeated, right? We said we could do it graphically by applying the vertical line test, right? So once we've kind of established that something is a function, well then there are some specific types of functions, right? And what we say a one-to-one function, right, is a function. So the first part is it's a function. So this stuff already has to be true, meaning every input is going to return exactly 1 y, right? But it's a function, right, where every output value corresponds to exactly 1 input. So what it's saying on a one-to-one function is this argument goes both ways. So for any x value you plug in, you'll only return 1 y, and for any y value you set the function to and solve for x, only 1 x comes back out, right? So let's look at an example of 2 functions that we've worked with before and kind of see this in practice. So I want to compare these 2 functions. So the first is going to be the line y equals 2x plus 3. And the second is going to be the parabola, right, x squared plus 1. All right, so both of these are functions, right? They pass the vertical line test. You can see that if you draw a vertical line and slide it back and forth, it's only going to cross it 1 time, right? But only one of these functions is one-to-one, right? So the question is, well, does it work the other way? So if the vertical line test, right, tests every x value, and if it crosses once, it shows you the y, well, then we can do something called the horizontal line test to test all the y values to see if there's only 1 x returned. So if you look at this, right, and I draw a horizontal line across here, right, and we slide it up and down, you can see that it's only ever going to cross the function 1 time, right? And then we know it's also going to pass the vertical line test as well. So we would conclude that this line, right, is 1-to-1. The parabola is a different story, right? It's going to pass the vertical line test, but it's going to fail the horizontal line test. So while it is a function, it's not a one-to-one function, right? And so one-to-one, you can kind of think of 1x, 1y, 1y, 1x. It's only supposed to cross it one time. So this passes, right, both the horizontal and vertical line test. This fails the horizontal line test, so it's not 1-to-1. And does anybody have any questions about what we're saying 1-to-1 means or why we're using this test? Because we're going to do a bunch of stuff with it, and I want to make sure everybody's cool in the definition for you. All right. Okay. So what you're going to see in here is very often when we, and kind of moving forward, once we start introducing the idea of inverses and 1-to-1, you're going to notice, and this was something that'll also come up on calculus, you're going to notice that attributes, right, that have to do with the input values on the original function are going to correlate to, they're going to have the opposite effect when we start talking about the inverse function. So you can kind of already see that here, right? If you want to test the use of vertical line test, testing all the possible x values to go in to test if something's a function, well then it should make sense you would use a horizontal line test to test all the y values if you're looking at something coming out. So this is an idea that you're going to see quite a bit in here. All right, so if a function is 1-to-1, right, then we now have the possibility that it might be invertible. So right now, for either one of these functions, if I want to pick a y value, let's say 4, right, and I wanted to know what x value correlates to 4, well, I could graph it and read across the graph and maybe find that value. Or algebraically, I could set each equation equal to 4 and hope only one x comes out. So on this graph, we would see 4 is probably about right here because its intercept is 3, so that's going to be 3. So then 4 is here, and you can see you're only going to get one y value or x value return, right? Over here, if we set this graph equal to 4, well, it would return 2 x values. So we could even algebraically verify that this is not a 1-to-1 function because only one value should come out if I do it, right? But what if I want to talk about all the y values and x values? I want to switch them up. So it may not be efficient to just set things equal to a bunch of random numbers. So we could actually come up with an equation that allows you to plug the y values in and see the x value come out. And so we call that equation the inverse function. Okay, so we say that a function f of x well, let me do this, is 1-to-1. Let's do this first. If, and so what I want you to see here, this is a little notation that you want to make sure you understand. It looks like a superscript. It looks like an exponent -1, right? But notice it's on the function itself. That means inverse function when you see that -1. And that does not mean 1 over f of x like it does for a normal exponent. This is just a way we notate the inverse function. So this is a function f of x is 1-to-1. If its inverse, so I'm just going to write inverse here, exists and is also a function. So this is another way we can test for something being 1-to-1, right? We could graph it and look at it using the horizontal line test, or we could try to calculate its inverse, and I'm going to show you how to do that in a second. And if the inverse exists, meaning you can algebraically come up with it, right? And that inverse function, when you graph it, is also a function, That's another way of verifying that it's one-to-one. Now, we were testing for that up here using the horizontal line test. So what the inverse function does a couple of things, right? Oops, can't spell today. So the inverse function algebraically is a rule right? It's a rule that lets you switch the input and output variables. So if we want to find the inverse algebraically, and we're going to do an example of this, we usually swap x and y and solve for the other variable. And so when you compare the two functions together, the original function lets you put the x values in and the y values come out. The new function will accept the y values and you plug in and solve rather than having to set it equal and solve. Graphically, what happens is f inverse is the original graph reflected over the line y equals x. So if you were to graph an inverse and its original function on the same graph, and we draw the line y equals x, it would look like a mirror image of itself around that line. Whereas, we said when we reflect about the y, right, that created a mirror image about the y, we reflected about the x, and that created a mirror image there. So, and I want to make a note before we start playing with some examples. Some functions are only invertible if you restrict the domain to make it one-to-one. So all one-to-one functions should have an inverse, because if we flip their x's and y's, right, they'll still only return one value back, and that was the whole deal. In order to be an inverse, you also have to be a function. So if it's one-to-one, it's definitely invertible. But some things, right, algebraically may look like they're invertible, but when you graph it, you realize they weren't actually one-to-one. So we might have to restrict it. So believe it or not, this guy right here, I could come up with an inverse function, but I'd have to restrict the domain first, because right now it's not one-to-one. So if I were to flip this guy over the line y equals x, it would turn this way, right, and fail the vertical line test. So there's a way we can restrict it down, and I'm going to show you how to do that. So let's look at finding some inverses of some functions. So let's start with something really simple, right? We had our line, we saw its picture, we know it's one-to-one, so this thing should have an inverse. And since it's a line, and it's pretty easy to work with, let's go one step further before we actually do this, and let's look at the domain and range of this. So it's a line, right? So the domain is all reals, and the range is all reals. So that means any value of x is allowed to come in, any value of y on the number line is allowed to come out. Furthermore, since we visually saw this as one-to-one, every single one of those values in the domain will correspond to exactly one value in the range and vice versa, right? So if we tell you that the inverse is the line reflected over the line y equals x, and we said the inverse function allows you to plug in the original outputs to then return the inputs, then algebraically when you want to find an inverse, the very first thing you want to do is rewrite the equation switching x and y. So you trade all the inputs for outputs and vice versa. So every x you rewrite as a y, every y you rewrite as an x. If the variables have other names, then you swap those names, all right? So if it's like v of t, for example, right, then all the t's become v's, all the v's become t's. Then you solve, right, the new equation for y if possible. So step one there, when it says switch x and y in the equation, that is literally trading the domain and the range, right? Because you took all the original input values and put them where the output should be, and you took all the outputs and put them where the input should be. So when you solve this new equation, it will now accept the original range and give out the original domain. So on an inverse function, one of the properties we're going to see when we go through these examples is that the domain and range should switch with each other, unless we've had to do some special domain and range restrictions. So this is what I was kind of hinting at earlier when I said algebraically, we'll just ask you to find the domain of functions, but it's really hard to just throw a random equation at you and say, give me the range back if you don't know what the graph looks like. But if you know that that function's one-to-one, you can look at the domain of the original function. That's easy to do. We have an algebra rule for that. Then if you can find the inverse, well, the domain of the inverse is the range of the original function because they switch back and forth. So there is a tool now to finding the range, but only on certain types of functions, right? So when we do this, let's set this up. So step one, right, says let's rewrite the equation, but we're going to swap the x's and y's. So now it's x equals 2y plus 3. Then we're just going to solve this for y. So x minus 3 equals 2y. So 1/2 x minus 3/2 equals y. So I was able to find the inverse, right? And I can see that it is also a line. And if it's a line, well, then I know lines are functions. So this function existed. And it's also, or this equation, I was able to solve for the inverse existed, and it was also a function. So I know that that original equation was one-to-one. I knew it by looking at the graph, but this is a way algebraically I can determine it as well. So if I were to graph these two lines, oops, on the same graph, well, here's what would happen. Right, here was the original equation, and here's the line. Oh, I should have made this steeper. Sorry guys, I didn't do my slope right. I should have drawn y equals x first. 2x should have a much steeper slope. It should be something like this, right? If that line has a slope of 2 and the dotted line only has a slope of 1, it should be much, much steeper. So that would be my line 2x plus 3. Well, what was the slope of my inverse function? 1/2. Well, 1/2 is very, very small. It's actually kind of close to 0. So if I were to graph my inverse function on this graph, it's taking this line and reflecting it over this dotted line, reflecting it over the line y equals x. So it would look something like this. See how it makes like a mirror image around that dotted line? And that's what we mean by it's reflected over the line y equals x. And the reason we use the line y equals x is because we're swapping all the x's and y values. So if so 0.03 is on the graph of f of x, right? If you plug 0 into the red line, 3 comes out, right? Where would that point be on the blue line? Does everyone take a guess?
It's the y-intercept.
Well, what was the very first thing we did in the algebra before we come up with the equation? What did we say the inverse does?
Rewritten and swapped with x and y.
It swaps the x's and y's, right? So if 0 goes into the f of x and 3 comes out, then the inverse function means if you plug 3 in, 0 comes out. So if you know the point on the original function and you know the inverse exists, then the x's and y's swap. So if you had a table, if your function was a table, and we told you, assume the inverse exists, now give me the inverse function on a table, well, you would simply rewrite the tables and switch the rows. You would make all the y's the input, all the inputs the outputs. That's what we do, you swap them out, right? Now on this one, it's a little trivial, but if we looked at the domain and range, right, of the new line we created, well, it technically swapped. Now they happen to be the same, they happen to be all reals, but it still comes back as both of them are in fact all reals. So if I give you any point on a function without even knowing the equation, you should be able to tell me that point on the inverse function because conceptually you switch the x's and y's, right? If you don't have the algebra at your disposal because maybe you don't know the equation of the graph, well, you can identify some points on the graph, plot them with their x's and y's reversed, and then connect the dots and kind of see that that's what it should look like. So also, geographically, it should be the mirror image over the line y equals x. You can flip it over y equals x as well, right? So let's look at another one. So let's look at the function y equals the square root of x. So the graph of this guy looks like this. We've worked with this before. This was on our graphs you should know sheet. And we know that at the origin, right, that point is 0, 0, because the square root of 0 is 0. So its inverse is not going to be just flipped over the x-axis. Its inverse gets flipped over the line y equals x. So the line y equals x looks like this, right? And one of the points on this graph is 1, 1, right? If you plug in 1, you get back 1. Another one of the points on this graph is, let's say, actually 1, 1 would be here, my bad. Right? Then we have another point here, let's say that's 2 or 4, 2, right? Because if you put in 4, you'll get the square root of 2. So if I were to plot these graphs and swap it, the inverse function would look like this. See how it mirrors the dotted line? That's what you do. You reflect it over the dotted line. So 0, 0 would come back on itself. 1, 1 would land back on itself. But then up here, right, this would be point 2, 4. So it's going to grow, instead of growing horizontally very rapidly, right, as you have to keep going further out to find another square, now it's going to keep going vertically up. So if we want to algebraically try to find the equation for this function, well, the first thing we do is we rewrite the equation, right, by swapping the x and y's. Then I'm going to solve this for y. And this is what I get. So if you look at the graph I drew, right, this looks like a parabola, is what came out, right, y equals x squared. But when we drew it, we only drew half the parabola, okay? And so here's where you got to be careful about your domain and range. The domain of the original function was 0 to infinity. And the range of f of x was 0 to infinity, right? Because you couldn't have any negative numbers under that radical. So if I take the inverse of this function, right, well, it can't be the entire parabola because no y values were in the range of the, or no negative values were in the range of the original function. So this is an example of where we would have to restrict the domain. So it's this inverse function, but only where x is greater than or equal to 0. So you would only accept the right half of the parabola. Conversely, if we started with y equals x squared, well, that's not 1 to 1. Doesn't have an inverse, right? Because if you invert it, it would fail the vertical line test. It would not be a function. So, but if you restricted the domain down to maybe only the positives or only the negative side of the function, then it is a 1-to-1 function, and then you could invert it, and you would either get plus or minus the square root of x when you did the equation back. So you want to make sure you're being careful when you're doing inverses and that you don't have to do some kind of domain restriction. So there were some examples the last time I taught this class, we did WebAssign, and there were problems in WebAssign where we actually asked you to understand where the domain restriction is. So I'm not really sure how Alex is going to do that quite yet. I'm going to look it up this evening if I can see if I can hunt around and find it. But on a parabola, the natural chopping spot is at its vertex. You just take one half or the other half. But once you accept the vertex and any point beyond it, the function starts turning again, and that's where you're going to run into that failure of the vertical line test. So if you're looking at something and they're asking about domain restrictions, the vertex is the natural chopping point on a parabola. All right, so let's look at another one. Let's say I want to know, right, is this invertible? If so, find the inverse. And we want to see what's happening with the domain and range. Oops. So we should be able to fairly easily figure out the domain of this function. So what value of x is not allowed to plug into f of x? 1, right? It's got a denominator. The numerator's fine. It's just 1, right? It's got a denominator of x minus 1. So clearly, if you tried to plug 1 into this function, you get a 0 in the denominator. So the domain, right, of f of x is going to be all reals, right, except the number 1. So anything lower than 1 is okay. Anything bigger than 1 is okay. The range is a little difficult to see from this equation. So I just happen to know that what the graph of 1 over x looks like. And this is the graph of 1 over x shifted to the right 1 unit because x minus 1 was plugged into the function. So I'm going to go ahead and draw it. And I'm going to tell you that I know, just because I knew ahead of time, so we're going to cheat, I know the range of this function is all reals except 0, okay? Now, what I'm going to propose to you is we're going to see that this function is 1 to 1. We're going to find its inverse, and when we calculate the domain of the inverse, it should come out to be all reals except 0, because the domain and range are supposed to switch on the inverse. So we said that this thing does not exist at 1, so what that actually means is it's going to have a vertical asymptote at x equals 1, and this function, use a different color here, is going to look like this. So you can see on the graph, right, it's all numbers but 1. That's where the asymptote is. There's a break there. And there's another horizontal asymptote at 0, so that's why 0 will never come out of this function, right? Now, this thing is 1 to 1. It passes the vertical line test, so it's a function. It also passes the horizontal line test. So even though these look like horizontal pieces here, they're actually slowly decreasing. So it does pass the horizontal and vertical line test. So this is a 1 to 1 function. And since it's 1 to 1, it should have an inverse, and we should be able to find it algebraically. So let's see, and I'm going to also bet money that the domain of the inverse will be all reals but 0, okay? So if we set the original equation, right, it was y equals 1 over x minus 1. So now we're going to say x equals 1 over y minus 1. And now I'm going to solve for y. So we'll multiply both sides by y minus 1. Then I'm going to divide both sides by x. And then I'm going to add 1 to both sides. Now, it's kind of hard in this form. Well, it's actually, no, it's fine in this form. So if you look at this function, what value of x doesn't work now? 0. So this is the inverse function. And the domain of this inverse is exactly as expected. It equaled the range of the original function. So that means the range of this equation is the domain of f of x. So this is a way, when in this section, you'll see a lot of times, we'll start saying give us domain and range, and they'll just give you an equation. So the domain you do the normal fashion way, right? But to return the range, a lot of times one of the tricks they're hoping for is, do you recognize that it's invertible? Find the inverse and find the domain of the inverse, and that gives you the range of the original function. Because all we did, step 1, was trade the domain and range. So that's one of the ways I was telling you earlier that kind of down the road we can kind of have a little bit of a sneak to figure out the range of something algebraically. All right, so I had another example I wanted to do. Sorry. All right. All right. So with this one, right, we want to find the domain and range and the inverse if it exists. So this is the graph of the square root of x, shifted left 5 places, and flipped over the x-axis. So it's y values are negative everywhere, right? And it's just shifted over a little bit. So if we want to know what the domain of this function is, we could try graphing it, or we could say, well, let's set the inside, right? Everything inside the radical has to be greater than or equal to 0. So x is greater than or equal to -5. So the domain is -5 included up to positive infinity. All right, and let's just say for a second here that I don't know what the range looks like, but can anyone picture the graph and figure out the range? Negative infinity to 0. So remember we looked at square root of x, right, was right here, this red line. So if we just take it and slide it over 5 spaces to the left, right, and then flip it upside down, it would curl this way. So it would be negative infinity up to 0, all right? So that is correct, right? Now when we find the inverse function, the domain of the inverse should be negative infinity up to 0, okay? So let's try to find the inverse here. So the first thing we do is rewrite the equation swapping our x's and y's. And we want to solve this for y. So the only way I'm going to be able to solve for y is I got to get y out of that radical. And the only way to get rid of a radical is to square it. So we're going to square both sides of this equation. So the -1 in front of the radical became a +1, and the radical disappeared because when you square a square root, it goes away, right? Then we'll subtract 5 from both sides. So once again, we get a parabola, and that is just the equation of a parabola shifted down 5 units. So that looks like a big U. But because we started with a square root, we actually need to restrict the domain of this guy. And so its vertex is at 0, -5, right? I can see that because this is technically in vertex form. So the domain of this guy, we would restrict this should be negative infinity up to 0, but hang on a second. Make sure my math worked out right here. Oh, yeah, sorry, I'm just reading this wrong. Yeah. So what we would do in this case is we would take the left half of the parabola, right? So in the previous example we accepted the right half of the parabola because the square root was giving us all the positive values. On this one, we have to take the left half of the parabola because it's a parabola that opens up, and when we flip it over the line y equals x, we want it to give us the negative square root values. So don't always assume that you're going to cut and take the right side, right? Because if you were to do this algebra the other way, it produced 2 radicals for you, positive and negative, and we wanted the negative case. So the domain says we'll take the left half, and then the range should be the domain of the original function. So let's see what happens when we graph these two guys. So the original function, right, we said we took the square root of x, we shifted it left 5 places, and we flipped it over the x-axis. This is a parabola that opens up and is shifted down 5 places, but we restricted it to the left-hand side. And so if we plug in -5, we should get 0, so it should touch here, a different color. So this should look something like this. Yeah, okay. Yeah, I know it looks funky, but when you flip it over this guy, it's going to push that point there, and then this is going to come back here. So let's see what it looks like if I graph it in Desmos. All right, so let's see if we do the negative. Where's my negative? Negative square root of x plus 5, and then we'll graph x squared minus 5. Yeah. Oh, okay, I see what I did. This should do this. It should cut up, but here you go. I'm going to show you on the screen. So this is our graph, right? There was negative, it actually did the same color too, I'm totally by accident, red and blue. So this is the original function. This is the entire parabola, but we only accepted the left half of the parabola. So when you flip the left half, right, you're going to get the negative case. If we had flipped the right half of this, it would have given us the positive case above it. So you want to make sure when you're working with parabolas that you understand which side of the parabola is going to give you the positive or the negative radical that you need. And when you can see it when you flip it over. Also, if you were to add a third function in here, let's graph y equals x, right? You'll see that whenever you're working with inverses, you always get the mirror image around that line. It should always look like it's reflected over that line, and that's how you know that you've graphed your inverse right. So I want to sum up just a couple things just to get so we know that functions that are one-to-one, right, are invertible. F inverse and f of x have opposite domain and ranges. And also that f inverse of x is the graph of f of x reflected over the line y equals x. And so algebraically, once again, when we have that two-step process, the very first step, when you swap x and y, as you're trading the domain and range, that's what's flipping it over the line y equals x, and then you solve to get the equation to see what comes out. So, and then just add one more little thing, beware of domain restrictions. So notice the only functions that we saw where we had to restrict the domain was because the function wasn't one-to-one, right? When you came out, like we had a parabola and that wasn't one-to-one, so we had to chop it off so it was.